Hello students, welcome to the class. So we are going to discuss in this video valence shell electron pair repulsion theory, which is abbreviated as VSEPR theory. The VSEPR theory, it is used to predict the shapes of the molecules. See, when octet rule failed to explain the geometry of the molecules, that is the shape of the molecules, so we know one of the limitation of the octet rule says that it cannot predict the shape of the molecules. To overcome those limitations, VSEPR theory was followed. Yes, so it predicts the geometry of the molecules from electron pairs that surround the central atom of the molecules. Okay. How it predicts, we'll discuss in this theory. Yes, the postulates are being given for this theory. This theory was first presented by Sidgwick and Powell in 1940. VSEPR theory is based on the assumption that the molecule will take the shape such that electronic repulsions in the valence shell of that atom are minimized. The valence shell electron pair repulsion theory, abbreviated VSEPR, it is based on the premise that there is repulsion between the pairs of the valence electrons in all the atoms. And the atoms will always tend to arrange themselves in the manner in which this electron pair repulsion is minimalized. This arrangement of the atom determines the geometry of the resulting molecule. Yes. The two primary founders of VSEPR theory are Ronald Nihlholm and Ronald Gillips. This theory is in their honor, it is also known as Gillips-Nihlholm theory to honor these chemists. According to VSEPR theory, the repulsion between the two electrons is caused by Pauli's exclusion principle that has greater importance than electrostatic repulsion in the determination of molecular geometry. Now, what does this actually mean? Continuously, I am saying that VSEPR theory, it is what I said, the geometry of the molecule, it is based on the fact that there is repulsion. Let me say it like this, as the name suggests. The name suggests VSEPR, valence shell electron pair. So it is something regarding electron pairs of valence shell. I have told in one of my previous video that whatever electrons, every chemical reactivity of an atom of an element is because of this valence shell configuration. And the electrons present in valence shell are called valence electrons. Yes, these valence electrons, there might be some electrons which are involved in bonding, and there are some electrons which are not involved in bonding. I cannot say for some atoms all the valence electrons are involved in bonding. Like for example, lithium, there is one valence electron and that is involved in bonding. It forms compounds like lithium chloride and all. Same with sodium chloride, sodium oxide, sodium hydride and all. But in some cases, all the valence shell electrons are not involved in bonding. So those electrons which are involved in bonding are called bond pairs. Yes, so I will denote it as, abbreviate it as BP, bond pairs. You can call them as shared electron pairs. You can call them as bonded electrons and all. And those electrons which are not involved in bonding are called as lone pairs. I will denote them as lone pairs, LP. Yes, you can call them as unshared electron pairs. You can call them as non-bonded electron pairs. For example, nitrogen. Nitrogen is having 5 valence electrons, but all the 5 are not involved in bonding, right? Only 3 are involved in bonding. So those 3 electrons which are involved in bonding, say with hydrogen, those 3 pairs I call them as bond pairs. And there are 2 electrons which are not involved in bonding. This is called as lone pair, which are not involved in bonding. So according to VSEPR, it says that the shape of the molecule is not only because of the bond pairs, it is also because of all the electrons of the valence shell. That's the name, valence shell electron pair. Repulsion. When we speak about bond pairs or lone pairs, see, bond pairs means what? There will be 2 electrons involved in one bond. Lone pairs means what? One lone pair, if I say, there will be 2 electrons involved. Yes. So electrons, finally, they are all electrons and all are negatively charged, right? So there will be repulsion amongst the like charges. This repulsion will result in the geometry of the molecule. Yes. So now the question arises, is our given molecule having only bond pairs? Then what will be the geometry? If it is having one lone pair along with the bond pair, what will be the geometry? Like for example, NH3, it is having one lone pair. If it is having more than one lone pair along with bond pairs, then what will be the geometry? For example, H2O, oxygen has got 2 lone pairs. Getting my point? So the geometry depends upon the valence shell electron pair repulsion. Therefore, the name valence shell electron pair repulsion theory. Getting my point? Okay. So let us see what are the postulates of valence shell electron pair repulsion theory. The exact shape of the molecule depends upon number of electron pairs, whether it is bonded or non-bonded around the central atom. So we are going to talk about the central atom. The electron pairs have the tendency to repel to each other since they exist around the central atom, and electron clouds are negatively charged. Yes, so they are negatively charged. There will be repulsion among each of the electrons. So when there is repulsion, when they are trying to move apart, they want to remain stable. So when they can remain stable, when they are maximum far away from each other. Yes, so to reduce the repulsion, they will take the positions in such that who will take the positions? The electron pairs will take the position such that they are maximum away from each other. So when they are maximum away from each other, the repulsion will be minimum. Yes or no? The repulsion will be minimum. So electron pairs try to take such positions which can minimize the repulsion between them. The valence shell is taken as a sphere with the electron pairs placed at maximum distance. Multiple bonds is treated as if it is a single electron pair, and the electron pairs which constitute the bond as a single pairs. Okay, so with this postulates, let us try to understand what it is actually trying to say. Fine. So what does VSEPR theory says? Let us see. First one. So I have to consider a polyatomic molecule. So in a polyatomic molecule, that is a molecule made up of 3 or more atoms, one of the constituent atom is identified as the central atom. For example, if I have NH3 molecule, nitrogen is central atom, because Lewis structure says that which is more electropositive, you have to place it at the middle. But if hydrogen is present, the other hydrogens will occupy the terminal positions. So this becomes the central atom. Water, oxygen becomes the central atom. CCl4, carbon becomes the central atom. Okay, you should identify which is the central atom to which all the other atoms are linked. Okay. Next, second point. The total number of valence shell electron pairs decides the shape of the molecule. So total number of valence shell electron pairs decides the geometry of the molecule. Okay. The electron pairs means what? They are all negatively charged. So the electron pairs have a tendency to orient themselves in a way that, so since all are negatively charged, there will be repulsion. So they will occupy the position in a space such that they will minimize the electron-electron repulsion between them. Therefore, when they are trying to minimize, like for example, I'll give you what this VSEPR theory says, that consider an atom as a sphere. It is a sphere. Consider an atom as a sphere. Okay. So if there is a bond, say I have a molecule, I should have at least 2 bonds to explain VSEPR theory. Okay. So only they say polyatomic molecules. So let me say I have molecule of type AB2 type. That means there are 2 AB bonds. Yes. So 2 AB bonds means those are electron pairs. You may say we will write it like this, or you will say we will write it like this. So when I'm writing it in different ways, those shapes are different, yes or no? Now, what is the correct manner? See, in both the cases, these are electron pairs. Here there are 2 electrons, here there are 2 electrons. Yes, so electron-electron repulsion will be there. These bond pairs, so what are they called? They are called bond pairs. So these bond pairs of electrons, they want to minimize their repulsion. Therefore, what they will do, they will arrange themselves. So central atom is my A. They will arrange themselves in this sphere in such a way that they will have minimum repulsion. So they will move like this. So much away. Yes. Other than this, can they have any other arrangement with minimum repulsion? No, this is the maximum distance away from each other so that the repulsion is minimum. So what the shape came out to be? The shape came out to be linear. The shape came out to be linear. If they are in linear position, then they will be at maximum distance away from each other, due to which there will be minimum repulsion. Therefore, I say the electron pairs, they have the tendency to orient themselves in a way that minimizes the electron-electron repulsion between them and maximizes the distance between them. Okay, so the valence shell can be thought as a sphere wherein the electron pairs are localized. on the surface in such a way that the distance between them is maximized. The distance between them is maximized. Should the central atom of the molecule should be surrounded by bond pairs of electrons, then a symmetrically shaped molecule can be expected. As I said, if the molecule is of type AB2, correct? If it is of type AB2, I'll get the shape like this. VSEPR theory, the strength of the repulsion is strongest if two lone pairs and weakest in two bond pairs. See, I will explain you how now. So this is a molecule with two bond pairs only. Correct? I'll take one more example. I'll say I have a molecule of type AB3 and how many bond pairs are there? 3 bond pairs are there. Correct? So how they will arrange to each other? They will arrange in such a way that they will have minimum repulsion. So I need not draw this here, it is understood. Okay. So they will arrange themselves in such a way that there is minimum repulsion and therefore maximum stability. So A is the central atom. So this is how they will arrange. Yes. So this is at maximum distance away from each other, all the 3 atoms. I cannot put 2 bonds like this and 1 bond nearer. No, they are at maximum distance away from each other. Yes, understanding. So what the shape comes out to be? The shape comes out to be trigonal. The shape comes out to be trigonal if the molecule is of type 3b3 with 3 bond pairs. Okay, if I have a molecule of type AB4 with 4 bond pairs only 4 bond pairs. Central atom is having only bond pairs. Therefore, the molecule will arrange in such a way, the bond pairs will arrange in such a way that they are at maximum distances away from each other. They are at maximum distances away from each other. Yes, when they arrange themselves in a sphere, valence shell sphere, then the structure comes out to be what? It comes out to be tetrahedral. It comes out to be tetrahedral geometry. And you can even say the bond angle also. Here the bond angle is 180 degrees. Yes or no? Angle between the 2 bond pairs. Here the bond angle, wherever you want to measure, the bond angle is 120 degrees. Here the bond angle is tetrahedral bond angle, we call it as 109.5 degrees. Yes. So if the molecule, similarly, if it is of type AB5, all 5 bond pairs only, then the molecule will arrange such that the 3 bond pairs are in one plane, B, 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 and 1 bond pair is above, 1 bond pair is below. Yes, this geometry, we call it as, see, when I draw this geometry, it comes out like this. Similarly here. Yes, this geometry is called trigonal bipyramidal. Bipyramidal. Getting my point? Yes. Similar. If I take AB6, it will come octahedral. It will come octahedral. So these are all the shapes of the molecules: linear, trigonal, tetrahedral, trigonal bipyramidal, octahedral. These are the shapes of the molecules when I have only bond pairs. When I have only bond pairs. Now, what if I have lone pairs? What if I have lone pairs? So in this case, I need to understand VSEPR theory in a more better form. Okay, how to understand it? See what we said. The geometry of the molecule depends upon the number of valence shell electron pairs. Yes, if the central atom is surrounded by bond pairs only, if the central atom is surrounded by bond pairs only, then it gives what type of shape? It gives symmetrical geometry. Symmetrical shape, you can see, because there will be only bond pairs. And what type of repulsions will be there? There will be only bond pair repulsions. Yes, if the central atom is surrounded by only bond pairs. If the central atom is surrounded by lone pairs, by 1 or more lone pairs, then I can expect bond pair repulsions or if there is only one lone pair, there will be lone pair bond pair repulsions also. And if there are more than one lone pairs also, there will be lone pair repulsions also. Yes or no? The lone pairs also might get repelled. Yes. The relative order of repulsion, where repulsion is more, lone pair repulsions are much stronger than lone pair bond pair, which are much stronger than bond pair. Now you may say, why is it so? VSEPR theory says this. This is the very most important postulate of VSEPR theory. It says among the order of repulsions, lone pair repulsions are stronger. That means the repulsions caused by lone pairs are stronger than bond pairs. The reason is, when we speak about lone pairs, see, let me say, I say this is the central atom and it is having these bond pairs. And there is a lone pair on the central atom. Bond pairs means what? Those are the pairs of electrons which are restricted to these two atoms only. Here, bond pair, restricted to these two atoms. Bond pairs, this is restricted to these two atoms. Lone pairs means what? Those are not involved in bonding, so they are free. They are free. Since they are free, they will occupy more space in the electron cloud. Therefore, the repulsions caused by lone pairs. Yes, so a lone pair is concentrated around the central atom. Lone pair, it is concentrated around the central atom, while a bond pair is pulled out in between the two bonded atoms. Understanding? Lone pair is concentrated around the central atom, whereas bond pair is pulled between the two bonded atoms. As a such, repulsions become greater when lone pair is involved. Repulsions become greater when lone pairs are involved. So till now, whatever examples we saw, AB2, AB3, AB4, AB5, AB6 types of molecules, there were only bond pairs. If there is at least one lone pair, as in case of NH3, nitrogen has got one lone pair, yes or no? Then the lone pair bond pair repulsions will be more than bond pair repulsions. So what will happen? So this lone pair bond pair, what it will do is, it will make the changes in the geometry. So the geometry will change. Yes, though if the molecule is of type AB3, expected geometry is what? Trigonal planar. But since the central atom is having one lone pair, the geometry will change. And that changed geometry is called distorted geometry. What it is called? Distorted geometry. So distorted geometry comes into context when there is one or more lone pairs. And you understood why these repulsions are stronger? Because lone pair is concentrated around the atom. So it is occupying more space. Whereas bond pairs, they are between the two atoms only. They are restricted between the two atoms. They are pulled between the two atoms. Therefore, lone pairs become, the repulsions of lone pairs become greater than the bond pairs. So if only one lone pair is there, there will be lone pair bond pair repulsion and bond pair repulsion. So what this lone pair does? This actually AB3 molecule, it will try to occupy itself like this. But because of presence of lone pair, it will push the bond pairs. And when it pushes the bond pairs come closer like this. Therefore, the shape, geometry of the molecule changes and disturbs, it gets disturbed. And that disturbed geometry is called distorted geometry. When the geometry gets disturbed, there will be change in the bond angle also. Yes or no? Yes, there will be change in the bond angle. So if only bond pairs are involved, symmetrical geometry is there. But if lone pairs are involved, it is distorted geometry. And repulsions, order of repulsion is lone pair repulsions are stronger. Then comes lone pair bond pair repulsions, and then comes bond pair repulsions. So with this, we can take an example of H2O molecule and NH3 molecule. So if you see in NH3 molecule, there are 3 bond pairs and 1 lone pair. So if there was only bond pairs, then expected geometry was trigonal. Correct or no? Trigonal geometry. But because of presence of 1 lone pair, there is lone pair bond pair repulsion, which is much stronger than bond pair repulsion. Therefore, molecule gets distorted. Yes, and the shape of the molecule comes something like this. All the hydrogens are in planar, but here there is what? There is a lone pair. So the molecule, the geometry comes out to be pyramidal geometry. And the bond angle here comes to 107 degrees. It comes to 107 degrees. Similarly with water molecule, H2O has got how many bond pairs? It has got 2 bond pairs. So expected geometry is what? Expected geometry is linear. So 2 bond pairs. But oxygen, the central atom, is having 2 lone pairs. it is having 2 lone pairs. So because of presence of 2 lone pairs, here lone pair repulsions are there, which are stronger than lone pair bond pair repulsions, which are much stronger than bond pair repulsions. All the 3 types of repulsions exist. Therefore, the molecule becomes, the structure of the molecule is not linear, it becomes bent. It becomes bent. So here you have 1 lone pair and here you have another lone pair. So geometry is bent, expected angle is 180, here it is 104. Understood? 104 degrees, 104.5 degrees basically. The geometry, the angle of bond angle of water molecule. Is that clear? So VSEPR theory, it predicts the shapes of the molecules. Yes, if there is multiple bond, it is treated as single bond. You can see here now. Molecule of type AB2E. So total number of electron pairs 3. Number of bonding pairs are 2. Lone pairs is 1. So if there is 1 lone pair, expected geometry is trigonal planar, but it is bent. This is the molecule. Then AB3E, there is 1 atom also. So 4. Then number of bond pairs are 3. Number of lone pair is 1. So expected geometry is tetrahedral, but the geometry comes out to trigonal pyramidal NH3 molecule. Similarly here AB2E2, 4 electron pairs, 2 bond pairs and 2 lone pairs. Yes, so E stands for lone pairs. Okay, so expected is again tetrahedral, but the molecule is bent, H2O, just now I have told you. AB4E, so there are totally 5 electron pairs, out of which 4 are bond pairs and 1 is lone pair. So if there are 5, we expect it to be trigonal bipyramidal as I have shown you, but it is distorted tetrahedral geometry, seesaw-like shape. AB3E2, 5 bond pairs are there, 5 electron pairs are there, out of which 3 are bond pairs and 2 are lone pairs. Out of 5, expected is again trigonal bipyramidal, but it is distorted T shape. Yes, AB2E3, see, totally 5 are there, 2 are bond pairs and 3 are lone pairs. I7 molecule. Yes, so it is linear. Geometry comes out to be linear. So this is about valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. So what does it say? It says about the, it tells us about the shape of the molecule. Shape of the molecule. Yes. Next concept, valence bond theory, or which is abbreviated as VBT. The valence bond theory, it was developed to explain the chemical bonding using method of quantum mechanics. Quantum mechanics. This theory primarily focuses on the formation of individual bonds from atomic orbitals of participating atoms due to formation of a molecule. Okay, so what is valence bond theory and what does it explain? Again, we have postulates. See, according to valence bond theory, let me tell here, electrons in the molecules, where they are present in the atomic orbitals rather than molecular orbitals. The atomic orbitals, whenever the 2 atoms are coming closer, see, whenever a bond is formed, it is valence shell which is involved in bond formation, right? So whenever 2 atoms are coming closer, whenever 2 atoms are approaching, the valence orbital, that is the atomic orbitals, they will come closer. When they are coming closer, they will overlap with each other. They will overlap with each other. So when the atoms are approaching together nearer, the orbitals of the atoms, they will overlap. Therefore, I said the atomic orbitals overlap on the bond formation. As the overlap is more, stronger will be the bond. This is what VBT says. Okay, let us see. Covalent bonds are formed when 2 valence orbitals belonging to 2 different atoms overlap each other. See, the orbitals must be half filled, because if they are completely filled, they will not overlap, right? They must be unpaired. To say valence orbitals half filled means unpaired. Electron density in the area between 2 bonding atoms increases as the result of this overlapping, thereby increasing the stability of resulting molecule. The presence of many unpaired electrons in the valence shell of an atom enables it to form multiple bonds with other atoms. The paired electrons present in the valence shell do not take participation in the formation of chemical bonds as per valence bond theory. So either it should have unpaired electrons, then only the orbitals will be involved in bonding according to valence bond theory. Okay, according to valence bond theory, the orbitals should have unpaired electrons, single electrons. If they are paired, it will not participate. If it is not having any electron also, it will not participate. Understanding? So there should be unpaired electrons in the orbitals. Covalent chemical bonds are directional and are also parallel to the region corresponding to the atomic orbitals that are overlapping. Sigma bonds and pi bonds differ in the pattern. Okay, let us first try to understand how they overlap. Then we will go to sigma bond and pi bond. So orbital overlap concept. According to orbital overlap concept, covalent bond formed between atoms results in the overlap of orbitals belonging to the atoms having opposite spin of electrons. See, it is shown here. Hydrogen at atom is having one electron, let me say here, and this hydrogen is having one electron. So 1s orbitals of each atom. When they approach together, there will be overlapping. Can you see overlapping of the atomic orbitals? When overlapping takes place, the hydrogen atom of this, the electron of this hydrogen atom and electron of this hydrogen atom, they have both unpaired electrons. So they will involve in pairing. Yes or no? They will involve in pairing. So formation of hydrogen molecule as a result of overlap of two atomic orbitals of hydrogen is shown here. So there is overlapping. Stability, and this new orbital which is formed by the overlapping of atomic orbitals, it is molecular orbital. So stability of a molecular orbital depends upon the extent of overlapping. If overlapping is more, strength is more. If overlapping is less, strength is less. Okay. So what are the main points of orbital overlap theory or valence bond theory, you can say. You can call it as VBT or you can call it as OOT, orbital overlap theory. It was being developed by Hitler and London in 1927 and later it was modified by Pauling and Slater. Okay, they both modified it. Fine. Okay, what it says, as we have discussed the postulates. To form a covalent bond, atoms must come close to each other. Yes or no? If a covalent bond has to be formed between the two atoms, those two atoms must come close to each other. They must come close to each other. Yes, they must come so close to each other that their orbitals must overlap. Which orbitals? Not all. Valence orbitals must overlap. So, to form a covalent bond, the two atoms must come close to each other so that their orbital of one overlaps with the other. So, there will be overlapping of the orbitals, correct? Or merging of the orbitals. Second point, orbitals having unpaired electrons of anti-spin, different spin, overlap with each other. So if this is having unpaired electrons, then only they will overlap. If this is having paired, it will not overlap. Understanding? If it is having paired, it will not overlap. So it should have unpaired electrons for overlapping, and that too with opposite spin. After overlapping, a new localized bond orbital is formed, which has maximum probability of finding the electrons. So maximum probability of finding the electrons is here. So a new localized bond orbital will be formed and maximum probability of finding the electrons it will have. I will represent it like this. Yes or no? 2 electrons. Getting my point? Covalent bond is formed due to electrostatic attraction between the radii and accumulated electrons, and by attraction of spins of two anti-spin electrons. If this is having clockwise spin, this will have anti-clockwise. Both should have different spins. They should contain unpaired electrons. They should have different spins. And they should come close to each other so that their orbitals will overlap. And the new bond orbital formed, it will have maximum probability of finding the electrons. Clear? Greater the overlapping if the overlapping is more. What does that mean? See, suppose this is the bond formed. Okay, so if the overlapping is more, what does that mean? The bond length is less. So I can say greater the overlapping, lesser the bond length, Therefore, stronger the bond, correct? Stronger the bond. Yes, so greater the overlapping, lesser will be the bond length, more will be the attraction, and more will be the stronger the bond means what? Bond energy will be more. Bond energy will be more. And if bond energy is more, stability of the bond is what? Stability of bond is high. Yes or no? It is more stable. The bond is more stable because it is requiring more energy to be broken. Yes or no? The extent of overlapping depends on what? It depends on nature of the orbitals involved. Which type of orbitals are involved? Here I am drawing circular means what? There are s orbitals involving. Yes. So what type of orbitals are involved? That depends upon the that will tell us extent of overlapping. And nature of orbitals involved and what type of overlapping is involved. More closer the valence shells are to the nucleus, more will be the overlapping. So if there is nucleus and there is this shell which is involved, if 1s shell is involved, overlapping will be strong, yes or no? Because nuclear attraction will be more. So in both the cases, if 1s shell is involved, overlapping will be strong. So more close the valence shells are to the nucleus, more will be the overlapping of, and the bond energy will also be high. Between two subshells of same energy level, the subshell more directionally concentrated shows more overlapping. So I can say directionally which is more concentrated, S subshell. So S subshell doesn't come in first energy level. So I will say 2s overlapping will be more than 2s 2p overlapping, which will be more than 2p overlapping. This is not much directional, right? They are in all the axes. Therefore, this is more directional, circular. It is same in all the distances, equal from all the distances, right? So 2s overlapping is more than 2s 2p, and then which is more than 2p 2p. Why? S orbitals are spherically symmetrical, and thus show. In this now, there are two types of overlappings. One is axial overlapping, which is also called head-on overlapping. And another one is parallel overlapping. Parallel overlapping. Yes. So we have axial and parallel overlapping. Let us see. Okay. Depending upon the type of overlapping, the covalent bonds are of two types, known as sigma bond denoted with this and pi bond denoted with sigma bond. Sigma bond is formed by end-to-end, head-on or axial overlap of the bonding orbitals along the internuclear axis. So it is head-on or end-to-end overlapping. The axial overlap involving these orbitals is of three types. Now you can see here. Yes. So s orbitals are spherically symmetrical, as I said. Yes. So s orbitals are spherically symmetrical. Therefore, they will only have axial head-on, or you can call it as end-to-end overlapping. Okay. Whereas on the other hand, p orbitals are directional, and thus they show either head-on or they show parallel overlapping. Parallel overlapping. Okay. So if it is axial or head-on or end-to-end overlapping, it will give rise to sigma bond. Sigma bond denoted with this symbol. And if it is parallel overlapping, it gives rise to pi bond denoted like this. So we have two types of covalent bonds, sigma bond and pi bond. So what are the differences between sigma bond and pi bond? Sigma bond results from end-to-end overlapping or head-on overlapping or axial overlapping. Yes, and in this case, axial overlapping or end-to-end overlapping or head-on overlapping can be between two s orbitals. It can be between s and p orbitals, or it can be between p and p orbitals. I'll show you how. Axial overlapping. Pi bond, it results from overlapping. Parallel overlapping is also called as sideways, or it is also called as lateral overlapping. Yes. So pi bond results due to parallel overlapping or sideways overlapping or lateral overlapping of two p orbitals. So p orbitals are only involved. For sigma, it might be SS, it might be SP, it can be PB. For parallel, for pi bond, it is always PP. Since s orbitals are directionally symmetrical, sigma bonds are stronger. Sigma bonds are stronger, whereas pi bonds are weaker. Yes, comparatively. So since sigma bonds are stronger, bond energy, if you see, it is, if carbon-carbon bond, if you see, it is 80 kilocalories. And here, it is around 65 kilocalories. So these are more stable. So since stronger bond, it is more stable, or I can call them as less reactive. Correct or no? More stable or less reactive. Here, since they are weaker bonds, they are less stable or more reactive. More reactive. Correct? These sigma bonds can exist independently. Pi bonds will only come when there is at least one sigma bond. So if there is between two atoms, if sigma bond can exist independently, but if you want a pi bond, there must be first a sigma bond, then only a pi bond can come. Let us discuss how. Okay. So in head-on overlapping, for formation of pi bond, I said it can be two SS orbitals involved. So can you see this? So two SS orbitals are involved. I call as SS overlapping. So what happens there? Two half-filled s orbitals, they come closer along the internuclear axis. See, this is along the internuclear axis. So they are coming closer along the internuclear axis. Therefore, I call it as axial overlapping. Yes, and they overlap, and that overlapping is called SS overlapping. Example. Yes, I can quote example for SS overlapping. Example is formation of H2 molecule. Yes. So hydrogen, it is having 1s1 configuration plus one more hydrogen atom, 1s1 configuration. So yes, they will come closer and it will form H2 molecule. So this is said to be SS overlapping. Second is SP overlapping, wherein one atom will use its s orbital and another one will use its p orbital. For example, HCl molecule. So here, hydrogen 1s1. Here, chlorine. Chlorine, you know, it is 287 and outermost shell unpaired electron is present in p. Therefore, 2p